Welcome to the 23rd lecture of the NPTEL MOOC on parallel algorithms. In the previous lecture, we have been discussing the connected components problem for the CR-EWP RAM. Let us do a recap of what we have seen. In the first step of the algorithm, for every vertex of the graph, we find the smallest neighbor. We do this using pointer jumping over the adjacency list of every vertex V. Therefore, this can be done in order of log n time. Then in step 2.1, if that is the smallest neighbor is smaller than V, then we set it as the parent of V. In step 2.2, we check if V has got children now. That is, if somebody has chosen V as the parent in step 2.1, that is checked in step 2.2. In step 2.3, if V has no child and no parent, then we pick some neighbor as the parent. So by now every vertex has got either a parent or a child, and the subgraph defined by these parent pointers will be a forest. That is, each component of it is a tree. Then in step 3, we do edge plugging. This involves sending the adjacency list of every vertex into the adjacency list of its parent. The entire adjacency list of the vertex is taken and is plugged into the adjacency list of the parent, while the parent does the same thing. Therefore, the adjacency lists of all the vertices in the tree will now be reachable from the root node. So the root node now has all the adjacency lists of all the vertices belonging to its tree. In step 4, we did pointer jumping. That is, every vertex redefines its parent, it adopts its grandparent as its parent. So this is done repeatedly until no further change happens. So this is done for order log n steps. So by now every tree has become a star. The star is what we call a supervertex. Then in step 5, we did a renaming. So if R is the root of vertex V's tree, V merges with R. That is, V is now losing its identity. V is going to be a part of the supervertex that is named R. Therefore, every edge which is originating at V and going somewhere will have to be renamed appropriately. So this renaming is done by informing every element within V's adjacency list that its new name is R. And then these elements, these adjacency list entries, will inform their twins of the same. Therefore, the presence of V in the twins also will be replaced with R's. Therefore, now at this point in time, all the adjacency list entries in the whole graph is renamed appropriately. So we will find only the names of supervertices in all these adjacency list entries, and all of them are present with the root of the tree, the root of the respective trees. And in step 6, This is what we were discussing at the end of the last lecture. We have redundancy removal. For this, in step 6.1, we list rank all adjacency lists. The adjacency lists which are now with the root of a tree, that is the super vertices, will be all list ranked, and then they are copied into an array. So, the elements will be appearing in this array in the same order in which they appear in the adjacency list. Then in 6.2, we apply Coles merge sort on each adjacency list, which is now in the form of an array. Therefore, we are able to apply Coles merge sort on it. So, now we will have all the copies of the same element appearing together. For example, if we have self loops of the form 4, 4, we will have many of them appearing together. Let us say we have entries of this sort with the super vertex 4. So, super vertex 4 has multiple entries of the form 4, 3, where 3 is also a super vertex. Then there are multiple entries of the form 4, 4, which are self loops, and then there are multiple entries of the form 4, 5, which are again edges into the super vertex 5. So, these are all redundant edges. We need to keep only one copy out of this set, and out of this set we need not keep anything. From the multiple copies of 4, 3, again we only need to keep one copy. How exactly do we manage it? For this, what we have to remember is that these elements are now available in an array, and when we know which elements are to be picked out of an array, we have a way of getting them together, which is compaction. So, first we have to mark all the elements that are necessary. All self loops can cross themselves out. Out of multiple entries of the same value, we pick out the first one and cross out the remaining. That is, the processor which is sitting on the second 4, 5 looks to the left and finds that that entry is also a 4, 5. Therefore, this 4, 5 is a duplicate and is not necessary. So, that processor marks itself. Similarly, this also marks itself, but the processor sitting on this 4, 5, when it looks to the left, finds that it is a 4, 4 to the left. Therefore, this is the first 4, 5. Therefore, this is chosen for retention. Similarly, the first 4, 3 is also chosen for retention, and the second 4, 3 is crossed out. So, in this way we can mark all the elements that are necessary to be retained into the next step. So, after marking all of them, we will do a compaction using prefix sums. This is an algorithm that we have seen before. This also can be done in order of log n time. So, now let us see how the graph looks like. Now, we have the super vertices. In the array V, we have some vertices marked out as super vertices, the remaining are all crossed out. They have all joined some super vertex or the other. So, we have some super vertices and some non super vertices, and every adjacency list entry has been transferred to the super vertices. So, these super vertices have adjacency list entries. The crossed out elements are without adjacency list entries. Now, what we have ensured is that these adjacency lists are without redundancy. Now, in this array of vertices, we can again apply compaction to get all super vertices consecutive and the crossed out vertices afterwards. So, this array with all of them having their corresponding adjacency list is what we are going to start the next iteration with. So, this is how the modified graph looks like. So, we can ignore all these vertices now, and the next iteration will continue with only this part of the adjacency list representation. So, every edge that is remaining here is between super vertices, and they have been named appropriately, and we have only the super vertices together in a compacted form. Now, we have got the graph in exactly the same form that we had at the beginning of the iteration. Therefore, we are ready for the second iteration. So, as you can see that this required order of log n time with n plus m processes on a CREWP RAM. Now, how many iterations are required? We get a clue when we look at the trees. Look at the hooking step. In the original graph, we ensure that every vertex gets either a parent or a child. Many of them, of course, will get both. Therefore, what we ensure is that every tree that forms has at least two vertices. This is the worst that can happen, vertices pairing off. If this is the case when we have n by 2 super vertices, this is the worst that can happen to us, which means the number of vertices reduces by a factor of 2. That implies that we require order of log n iterations. With each iteration taking order log n time, this implies order of log squared n time to reduce the graph to one that contains a number of isolated super vertices. So, we have several super vertices, but no edges, which means there is no further reduction possible. At this point, we have one vertex corresponding to every connected component. Are we done? Not quite. Finally, for the problem of connected components to be completely solved, what we require is that for each connected component, we need a star. We do not have a star yet. For example, in the first iteration, when several vertices join their super vertices and bow out of the algorithm, they all end up pointing to their chosen super vertex. So, V is the super vertex which survives into the second iteration, whereas V1, V2, V3, V4 are all bowing out. Similarly, you have another vertex U that is surviving into the second iteration as a super vertex. Several vertices have joined U. Now, suppose V and U belong to the same component and they join hands to form a tree in the second iteration. In that case, it could be that one of them or some other vertex belonging to their component survives into the next iteration. So, I am considering the case where neither v nor u survives into the third iteration, but some w survives, where w belongs to the same component as v and u. These vertices had bowed out in iteration 1, therefore, they did not participate in the second iteration. Therefore, at the end of the algorithm, they continue to point to u and v. But u and v participated in the second iteration and they bow out in the second iteration. Therefore, at the end of the algorithm, they end up pointing to w, and w at the end of the third iteration might point to some other vertex and so on. Therefore, what we find is that when the algorithm terminates, we have one single tree for each connected component. The root of this tree is the vertex in that connected component that survived the last iteration. Now, what do we want? We want to ensure that every component has one single star graph. How do we ensure this now? That's a simple solution: pointer jumping. Do pointer jumping for order log n steps. We ensure that every CC has a star graph. So now the algorithm has run in order of log squared n time using n plus m processors on a CR-EWP RAM. You can obtain an analogous result for the ER-EWP RAM as well, and later on this solution has been improved to an order log n time algorithm, again on an ER-EWP RAM, but those algorithms are much more involved and are outside the scope of this course. Therefore, we will not be going into them. So, for our purpose now, we can conclude this: the connected components of a graph can be found in order of log squared n time using n plus m processors on a CR-EWP RAM. Now, we will take up another problem. This is the problem of vertex coloring of graphs. There are various hues of this problem. Of course, the most restrictive of the problems is very hard to solve. For example, if you want to vertex color a graph with a minimum number of colors, then the problem is NP complete. So, we do not expect to find an efficient algorithm for vertex coloring graphs with the minimum possible number of colors. We will use far more number of colors and color the graph more efficiently. For example, let us say we are given a delta degree graph. What we mean by a delta degree graph is one where each vertex has at most delta neighbors. That is, the vertex degree of each node is at most delta. Such a graph is called a delta degree graph. It can be easily shown that such a graph can be vertex colored with delta plus 1 colors. So, let us see an easy sequential algorithm for this problem. Let us say the colors are one to delta plus 1, and we have an n vertex graph. The maximum vertex degree is delta. The sequential algorithm for this problem is very easy. Repeatedly you remove a vertex, and then suppose the vertex that we remove is V, then recursively delta plus 1 color the remaining graph G minus V. G minus V is the graph that we obtain by removing vertex V along with all its incident edges. So, this is a graph with one less number of vertices. By removing a vertex, you cannot of course increase the degree of any vertex. So, this is also a delta degree graph. So, inductively we assume that this can be delta plus 1 colored. So, G minus V is delta plus 1 colored, and then we put V back into the graph. But then when we reconstruct G, we find that V is the only uncolored vertex. All its neighbors have already been colored. All its neighbors have already been colored. But then V has at most delta neighbors. Each of these neighbors in the worst case can occupy one color. Of course, in usually it's much better because many neighbors could share a color, in which case we could have multiple free colors. But in any case, we can guarantee that vertex V has at least one free color. This is because there are delta plus 1 colors available to us in total, and V has at most delta neighbors. So, there is at least one free color. So, if delta happens to be 5, in this case we have used 6 colors, and when we look around in the neighborhood of V, we find that one color is missing, which is color 5. So, we can be given color 5. So, that is what our algorithm is. We remove a vertex. The rest of the graph is still a delta degree graph. It can be recursively delta plus 1 colored. You put V back in, and then color V. So, this is the inductive algorithm. The basis is when all vertices are removed except for one. So, there is only one vertex remaining, and when there is only one vertex remaining, we can give it any color that we want. Out of the delta plus 1 colors, we can give it any color that we want. So, this algorithm, all this does is to remove the vertices one by one and then put them back in the reverse order. So, the time taken by this algorithm is order of n if delta is order 1. If delta is bounded, then the algorithm runs in order of n time. Of course, in terms of delta, you can say it takes order of n delta time. That is because when a vertex is removed and is put back in, it has to scan its neighborhood. It can have an adjacency list of size delta. It has to go through this adjacency list to find the smallest color which is not in its neighborhood. This might take order delta time. So, on the whole, the algorithm runs in order of n delta time. If delta is order 1, this is order n. So, let us look at a parallel algorithm which solves this problem for bounded degree graphs. Let us say we want to delta plus 1 vertex color a delta degree graph on an ER-EWP RAM we assume that delta is order 1. So, the algorithm proceeds like this. In step 1, for each V of the graph, we do the following in parallel. There are delta iterations for each vertex. For each vertex, we attempt to define a predecessor as well as a successor. If the predecessor of vertex V is undefined, then vertex V proposes to the ith neighbor of V. What we assume is that vertex V has an adjacency list. The first element in the adjacency list is its first neighbor, and the second element is the second neighbor, and so on. So, in the ith iteration, what vertex V does is to propose to its ith neighbor. So, it is asking its ith neighbor to be its predecessor. So, the way vertex V is proposing to its ith neighbor, vertex V might be the ith neighbor of some other vertex. So, vertex V might get some proposal. So, if the successor of V has not been defined yet, it chooses one from the proposals received if any. Of course, it is not necessary for a vertex to receive proposals. In case it does not receive a proposal, there is nothing to choose from. It will not be able to choose the successor in this step. Let us say if V's proposal to its ith neighbor Wi has been accepted, then appoint Wi as the parent. So, once again what is happening is this: we are attempting to define a predecessor as well as a successor for every single vertex. For every vertex we have delta iterations. If the predecessor of vertex V is not defined yet, then it will propose to the ith neighbor of V. V will propose to its ith neighbor. So, this is happening synchronously. So, every vertex is proposing to its neighbors in this one step. So, this is, let us say, step 1 1. So, in step 1 1, every vertex is proposing to its ith neighbor. In step 1 2 of the ith iteration, the vertices are mulling over the proposals it received in step 1 1. It's if for a vertex V, if its successor is not defined yet, it chooses one from the proposals that it received in step 1 1. And then in step 1 3, it goes back to the proposals it made. If one of them has been accepted, if it has been accepted, it has made exactly one proposal in the step. If it has been accepted by Wi, which happens to be the ith neighbor of V, then P of V is set to Wi. It made the proposal only because its predecessor was not defined. So, once the predecessor is defined, it will not be making any more proposal in the coming steps. So, this is what step 1 involves. A vertex makes multiple proposals until it gets accepted as a successor. So, a vertex is appealing to its neighbors to take it on as a successor. So, if somebody agrees, then that vertex will be chosen as V's predecessor. Similarly, V receives multiple proposals. If it receives a proposal, it will choose one among them as its successor. And once the successor is chosen, the successor will not be redefined. So, a vertex will get at most one successor and at most one predecessor. It is possible that a vertex receives neither a successor nor a predecessor in this step. When does that happen? If all of V's proposals are turned down, this can happen because in the first step V appeals to its first neighbor. It's turned down because this neighbor has chosen somebody else as its successor. V has appealed to the second neighbor W2 in the second step. Again, this was turned down because W2 turned elsewhere. Likewise, it has gone through all its neighbors and all of them rejected the proposals of V. In that case, V becomes unable to define a predecessor. So, we might end up without a predecessor. Similarly, we might end up without a successor as well. That happens when all of V's neighbors get accepted elsewhere. That is, in the adjacency list of these neighbors, V happens to be rather way down, and all the neighbors of V get accepted before they come to V. For example, if V happens to be the 10th neighbor of all its neighbors, then and all of them get accepted, let us say, by the 9th round of proposals, then we will never get to choose a successor. So it is possible that V has neither a predecessor nor a successor. So in this case, V has no successor and no predecessor. Now let me define LP as the subgraph induced by the successor predecessor pointers. So here each vertex gets one successor and one predecessor at the most. A vertex gets at most one successor and at most one predecessor. So if a vertex V happens to get a successor as well as a predecessor, then its vertex degree is 2. If it either misses a successor or misses a predecessor, then its degree is 1. If it is isolated, that if it is neither with a successor nor with a predecessor, then its degree is 0. Therefore, in this graph LP, the vertex degree of any node is at most 2. So LP is a degree 2 graph. The vertex degree of any node in LP is 0, 1 or 2. That is why we call LP a degree 2 graph. So what would LP look like? A graph in which every vertex has a degree of at most 2 will have this form. If in a component every vertex has a degree of exactly 2, then it will have to be a cycle. If a component has degree 1 vertices along with some degree 2 vertices, then that will necessarily have to be a degree a chain. So this is a cycle, this is a chain. If a vertex has no degree, it is an isolated vertex. So LP is a graph of this form with cycles and chains and isolated vertices. Now what we do is this. In step 2, we form G minus LP. G is our original graph and LP is the graph that has been formed just now, and then we form G minus LP. So once again let us consider LP. LP consists of cycles and chains and isolated vertices. So this is what LP is. So these are all edges belonging to G. So some edges of G have been picked out to be in LP. These edges define the subgraph LP. So LP consists of chains and cycles. If you add the remaining edges, we will get G minus LP. So G minus LP has the same set of vertices, but a different set of edges. To signify that it has the same set of vertices, I am superimposing the two vertex sets. The vertex set of G as well as the vertex set of LP are identical. Now the edges of G minus LP I will draw in red. These could be the edges of G minus LP. The original graph G could be like this. Here the black edges are the edges of LP and the red edges are the edges of G minus LP. When you put them together, we have the original graph G. So, both LP and G minus LP have the same vertex sets. G minus LP and LP have the same vertex sets, but disjoint edge sets. LP is a 2-degree graph, G minus LP is a graph with delta plus 1 degree again. That is because some of the vertices of G minus LP could be isolated in LP. That is, if a vertex is isolated in LP, then in G minus LP it has not lost any degree from G. Therefore, it retains its vertex degree of delta plus 1. So, here what we do is to, in step 3, we color LP with 3 colors using the list coloring algorithm. And let us say we recursively delta plus 1 color G minus LP. G minus LP is a delta plus 1 color, the delta degree graph, but it has fewer number of edges. So, it should be possible to delta plus 1 color it. From the sequential algorithm, we know that it is indeed possible to delta plus 1 color it. So, we recursively delta plus 1 color it. We shall see how far the recursion will go. First, let me describe the algorithm, then we will do an analysis and see how far the recursion will go. So, we have recursively delta plus 1 colored G minus LP and we have colored LP. So, when we put G minus LP and LP together, we get the original graph. But then what we find is that the graph has, the vertices of the graph has got 2 colors each, one from the coloring of G minus LP and one from the coloring of LP. G minus LP has been delta plus 1 colored and LP has been 3 colored, but the two graphs have exactly the same set of vertices. Therefore, these vertices are going to get 2 colors each, one from the coloring of the delta plus 1 coloring of G minus LP and the other from a 3 coloring of LP. So, we can take an ordered pair of these colors. Let us say vertex V gets color alpha in the delta plus 1 coloring of G minus LP and gets beta in the 3 coloring of LP. Let me take the ordered pair alpha beta and call this a color. Now, this becomes a color for G. This is a valid color for G. That is because when you take 2 adjacent vertices of G, they cannot have the same ordered pair as its color. When you take 2 vertices, 2 adjacent vertices, if they are not adjacent in LP, it could be that LP gives them the same color. Therefore, its second component could be identical, that is, both of them could be beta. But then, since they are adjacent, the edge between them falls in G minus LP. Therefore, in G minus LP, they got different colors. So, if the first component here was alpha, here the first component will have to be some other alpha prime. Therefore, if the edge between them falls in G minus LP, then their eventual colors are different. Similarly, if it falls in LP, then again their colors are different. If they are not adjacent in G minus LP, they might get the same color alpha in that, but then they will get different colors beta and beta prime in the 3 coloring. Therefore, no 2 adjacent vertices will get a valid will get the same coloring under this. Therefore, if you form colors in this fashion by taking ordered pairs of the 2 colors, we get a valid coloring, but then we would be using far more colors than we are prepared to use. How many such ordered pairs could there be? The first component of an ordered pair is one of the delta plus 1 colorings. So, there are delta plus 1 possible values for alpha. Beta is one of the 3 colors. Therefore, there are 3 possible values for beta. Therefore, the coloring of G, this coloring of G uses 3 into delta plus 1 colors, whereas we are prepared to use only delta plus 1 colors on the whole. But then you can reduce the 3 into delta plus 1 coloring into a delta plus 1 coloring. What we do is to consider all the colors from delta plus 2 to 3 into delta plus 1 one by one. First, I consider all vertices of color delta minus 2, delta plus 2. We consider all vertices of color delta plus 2. There cannot be an edge between them in G because the coloring is valid, therefore, no two adjacent vertices could get the same color. Therefore, this will form an independent set. Let us assume that we have one processor sitting on all these vertices. This processor will look around and replace this with the smallest color not in its neighborhood. Its neighborhood has a size of delta at the most, and we have delta plus 1 colors to use. So, there must be one color which is not in the neighborhood. So, this vertex will adopt one such color. Similarly, will this vertex and this vertex. So, all vertices of color delta plus 1, delta plus 2 have now colored themselves with one of the valid colors. The valid colors are ranging from 1 to delta plus 1. So, now we are done with all vertices of color delta plus 2. They have been assimilated into the coloring that we want. Now, we consider all vertices of color delta plus 3. They will also form an independent set, and we can do likewise. The processor sitting on them will look around in order delta time and pick the minimum color which is not in the neighborhood for these vertices. So, these vertices are also colored. Likewise, when you run through all the excess colors, the excess colors are from delta plus 2 to 3 into delta plus 1. So, we have order delta extra colors, but we have assumed that delta is order 1. So, when we run through all of them, then all the colors have been assimilated. Every vertex in the graph would have been colored with one of the valid delta plus 1 colors. So, the algorithm appears complete, except that we have to argue that the recursion works correctly. That is, after forming the graph LP, we removed LP from G and then formed G minus LP. Of course, we indeed know that G minus LP is a delta plus 1, a delta degree graph, and therefore is delta plus 1 colorable. But then will the recursive call color this appropriately is the question. We can see that this will work correctly, that is because in G minus LP, a vertex V that is isolated in LP has a degree of delta plus delta. That is, this vertex has not lost any of its degree in G minus LP. That is because it failed to get a predecessor or a successor in LP. But then why did it fail to get a predecessor or a successor? Because all its proposals were rejected by its neighbors and none of its neighbors made a proposal to it. And why did the neighbors refuse all its proposals? Because they had accepted somebody else's proposal. So, all of them got a predecessor. Similarly, all of them got a successor as well. Therefore, what we know is that if a vertex is isolated in LP, then that means all of its neighbors has lost at least one vertex degree. Therefore, this can continue for at most delta minus 1 steps. Therefore, when the recursion goes down to delta minus 1 steps, in delta minus 1 levels of recursion, this vertex is the only neighbor that its neighbors has. Its neighbors have no other neighbor after delta minus 1 levels of recursion. At this point, it will have to necessarily accept its proposals, and therefore its degree will start decreasing. Therefore, by that time we are ready to go down 1 degree. Therefore, the graphs that you get at that point can be colored with 1 fewer colors, and therefore the recursion works correctly. So, this establishes that the total time taken for coloring the graph with delta plus 1 colors is order of log k n with n by log k n processes. That is because in this algorithm the running time is dominated by the cost of coloring a list. A linked list can be 3 colored using our optimal algorithm that runs in order of log k n time using n by log k n processes. We have studied this algorithm before. So, using that algorithm we can color the linked list. The rest of the cost of the algorithm is all in the recursive calls, and the recursion runs only a constant levels deep. Therefore, what we have established is that the total time taken by the algorithm is order of log k n with n by log k n processes if delta is order 1. So, this is an algorithm for vertex coloring of graphs. So, that is it from this lecture. Hope to see you in the next lecture. Thank you.